Good morning, everyone. I got the cursed presentation slot before lunchtime, so try not to get distracted by when the food starts getting rolled out. Try and make the next 30 minutes as entertaining as we can, and we'll get you to lunch on time if we're lucky. For those of you I haven't met here before, my name's Rob. Most people here, both in this room and around the venue, will know me as Bok, though. One of the organisers for Melbourne Cocoheads. During the day, I am a principal software engineer at ANZ and the iOS platform lead for the ANZ Plus app. But more importantly, much more importantly, I'm also the founder of BokBank, the wonderfully facetious neobank that I introduced in this room actually last year. If you haven't heard of it before, I'm not sure where you've been, but BokBank is a highly secure and performant banking institution with a reputation for disruption, innovation, and trend setting. And it's great to be a part of it. Really is. In a few different places, I will pop the QR code up in one of the corners if there's more information. In this case, this is a link out to my presentation from last year, where we did introduce BokBank for the first time and spoke about its adventures in OpenTelemetry and instrumentation and all of that sort of stuff. Don't worry if you missed any of them. I have all of the QR codes on the last slide as well. So since last year, BokBank has skyrocketed. There are now millions of, let's call them valued customers, using BokBank for their everyday banking. And scaling to those levels has naturally brought its own series of challenges. And to give a little bit of context to that, I need to talk a little bit about the architecture first before we get into the meat of this. So BokBank is an offline first app. We cache the customer data securely and encrypted on the device, like account balances, transactions, to try and give you the best possible app experience that we can. The QR code for this one goes to a presentation I gave at Cocoheads back in 2022, so 3 years ago now, on the very similar architecture that the ANZ Plus app works off. If you'd like to learn more about what the team and I have done at ANZ, that's a really great place to start. Now, as for whether ANZ Plus inspired BokBank or BokBank inspired ANZ Plus, we'll leave that one for the lawyers to figure out. So, because BokBank has a number of different client applications, and all we expect our client applications to be fully featured, we haven't gone and built a BFF or anything retro like that. Instead, we take the microservices that power BokBank itself, and where appropriate, we make those APIs available directly on the internet to the clients to use. We also provide a cache and validation service that tells us when something's out of date, and when that happens, we just call the appropriate API to refresh that data. Customer sees it, and it works really well. When everything's going great, it works really fast, like 200 milliseconds response times. It's really good. But when we get to an outage, and even a small outage, it can hurt us quite a lot. So when you're synchronizing data behind the scenes, if you encounter a failure for your API, what do? You can't really show the customer or the user an error because they have no idea what you're doing behind the scenes. How are they going to have context to be able to understand the error and fix it in the first place? But you can't just ignore it either. You were told the data's out of date. If we continue to display that data without refreshing it, then we're willfully showing the customer the wrong information. So we have to retry it. But retries are selfish in general. Whatever it costs you to make that API request in the first time, if you retry it, it's going to cost you the same again, and then the same again, and then the same again, and the same again. So 3 or 4 retries you're paying, that's going to be a concern. You're paying several times the cost over and over again. And when you've got millions of customers and 20 to 30 different APIs that you might be integrated with, that really scales up real fast, and you've just DDoSed yourself. So in the golden old days of the internet, right, a DDoS was a malicious actor taking their well-crafted and finely controlled botnet, pointing at a target and flooding it with traffic to starve it of resources, use up all of its bandwidth, lock it out. Today, we all have millions of devices in our pockets, in our hands, and a poorly configured app can do exactly the same thing to your own backend. All right, so rather than just slides, I'm going to intersperse demos throughout this, because it's way better to explain things with pictures and code than it is with slides. So I'm going to talk you through my setup here first. On the right-hand side, I have a little internal testing tool that we use. It just starts up a little web server, so let's run that. We're listening on port 8080, good to go. And I've got this little control here to decide whether the APIs are going to succeed or fail, so we can simulate an outage. I've also got a little statistics view, which is where we'll spend all of our time, to help us graph the number of requests that are coming in, and this is all just Swift charts, so it's nice and easy. The number of different clients that we have as well, because we have multiple requests per client, whether the results are success or a failure, so we can see that as well, and whether it's a fresh new request or whether it's a retry, so we can see that as well. So wish me luck. Let's hope this doesn't rebuild from scratch. Shouldn't. I'll walk through the client first. So to test this, I've just got a little Swift test. We use a discarding task group to try and simulate a whole bunch of clients, 500 in this case from our first one. We smear them over the 15 seconds to try and simulate a period of sustained load rather than just throwing everything up front. And we're going to do about 30 retries, 30 requests per client. And then inside the task group, we add a task, run the client. Client, in this case, for the first demo, we're going to disable any retries. It will just drop them. But the client is just a HTTP client. Again, another task group for each of those requests, so we do them all in parallel. We execute the request. The request is just a HTTP GET to port 8080 and a little dev world thing that I've got set up, some headers so I can populate the stats. Especially this one, if it's a retry, we'll add a header so we can graph it appropriately. And then we just execute it. If we get a 200 back, great, nothing you need to do. If it fails, we schedule a retry, and if it throws an error, we schedule a retry. So that's all it is. So let's see how close I can get to DDoSing my own laptop. And hopefully that doesn't take too long to build. Great. So everything going well, we should see a bunch of traffic coming through. So we're sustaining somewhere around 1,000 requests a second mark at the moment. And we're on 43% CPU, 38% CPU. Good, so it's the same as when I tested it this morning. That means I can keep my numbers good. So that's it, right? That's the happy flow. I'll run it again, but this time we'll change it to fail. So you see they come up in red when they fail, and then we can do Harveys and whatever else we want. We'll keep that on fail now. So first thing I want to do is actually kill my laptop, because why not? But we won't do that with 500, we'll do that with 100. First thing we're going to do, getting the customer the most up-to-date data is the most important thing. Let's just retry as fast as we can. We want to get that through to them. So we'll change that to our immediate one. That won't succeed. And we run that, right? So we're running 500 clients instead of 100 clients instead of 500, so 20% of the traffic, 20% of the client load. But we're well up, we're above where we were before. So we're above 1,000 and we have flatline CPU. So that's great. So you can see at the bottom now, we've got retries coming through in orange versus the new requests in blue. That's never going to complete unless I turn it on. We can make it go like that, but yeah, that's enough for that demo. So we know even 100 clients, 1/5 of what I was doing is already causing way more contention on my CPU than it was before. So now that we've done that, and my laptop is still going, so that's the first hurdle cleared. The most common thing that people do here is reach for an exponential backoff. Whether it's actually exponential or not, it's usually a generic term that just means to delay successive retries by a certain number. Most commonly, we double, but it's not always double. So that's what So that's what you would do in this sort of situation, right? For the first one, because wider outages are uncommon, and it's probably just a local network thing, we can still retry that first request immediately, but then we would wait 1 second, 2 seconds, 4 seconds, 8 seconds, all the way out to infinite. Typically though, waiting an hour for a retry is a terrible customer experience. They have no idea when they're going to get their latest data. So you cap it somewhere that makes sense, often around 30 seconds. So you just retry no longer than 30 seconds. You would also typically here apply jitter, which is just a random additional amount of time that you might add or subtract to try and not have it be uniform. Because if you have 10 people try at t-0, those 10 people are going to retry at t1, t4, you know, it's going to be the same peak and trough all the way through. And if your limit is 5, you're going to have 10 still each time. So it doesn't really save much. This way, at least over time, it spreads out a bit more. So let's give that a go here. And I need to remember this time to go down and change this one to the exponential backoff one. We'll put a max delay in here of, say, 10 seconds. Otherwise, we're going to be waiting like 5 minutes for the demo to run. We don't want that. And I needed to, yeah. And what I'll do first of all is just run one request so we can see what the algorithm looks like. So we're expecting that immediate retry, then 1 second, 2 seconds, so on and so forth. Fingers crossed. So we can see we had that initial request, then one immediate retry, one after 1 second, one after 2 seconds, and then 4 seconds, and then it'll be 8 seconds or so, and then it should cap around the 10 mark. We don't need to stay there and watch that though. There we go. We can wait if you want. The more impressive demos are still to come. This is just the basics. So this is kind of the goal, right? If you want to go for the best we can possibly do, let's start with the exponential backoff of retries. There's nothing wrong with that. That's still industry best practice for slowing down successive retries. But we want some kind of mechanism to detect when there's a bigger problem, like, you know, much bigger than what we're handling, and to maybe shut things down. So we stop all of those individual retries as quick as we can, and in that way we protect the backend infrastructure from the denial of service attack, giving them hopefully time to recover and restore service to normal. But we also need some kind of way to know when things are back to normal, so that we can resume what we were doing before. But we also don't want to just jump straight back in and kill the back end as soon as we know that's happened, right? So it needs to be gradual. I'm sorry for anybody who is too young to get the Simpsons reference here, but this is kind of an in-joke at work, so it had to go on my slides somewhere. So third and last demo, hopefully the most impressive one. Before I describe how it works, let's look to see if it does work. Now I'm going to keep it as, oh hang on, I didn't even do the bigger demo before. That's silly. Let's do the bigger demo of the exponential backoff first. Skipped one. So this is the exponential backoff running at 100, right? So you can see we're back up to 1,000 as we go through. We've got the retries coming through as well. Once this stops with new requests, we should see a sustained level of traffic. Also around the 40 clients per second out of our 100. And then, you know, we drop to around the 400 mark or so, right? And that's just kind of where it stays. That's still 30 requests all retrying, but it spreads them out a little bit. So it was better than we had when we were DDoSing ourselves before. And our CPU is at 20%, so pretty good. All right, let's do this again. But this time we're going to go with the drinking bird one. Now this does some work in the background to manage those requests, which I'll explain later on. So we need this now. We'll just run that in a task, and then we'll cancel it and clean up when we're finished. So let's run that one. So for one client, we should expect to see the same exponential backoff that we had before. Hopefully. Should have waited for the graphs to finish. So there we go. So we got the one request at the start, and because of timing, it dropped into the next frame. But 2 seconds, 4 seconds, 8 seconds. So at one scale, it works the same way as an exponential backoff. We're not really adding a lot of value there. But let's go for the money shot. Let's go back to where we were before. So if we run full throttle with this, and I'll click go so I can talk while it's building, what we kind of want to see is it will start off the same way as the exponential backoff one does. CPU usage overall should be lower once we get past the initial requests. But the real money shot comes once we get past those new requests. The number of clients will stay the same, but the number of requests should flatline, which is coming up now. Cool, so that's worked. So we've got the same amount of traffic, the same amount of clients that we had before, but we're doing 1/30th of the traffic that we were doing before. And that's the minimum level that we can sustain, right? So it's gone really down. And it did it quickly too. But we can, when we turn it back on, it ramps back up. And when we turn it off, it ramps back down. And I'm not going to stay and play with that, but you get the idea, right? It reacts quickly to what's going on. All my demos were successful. Yay, that's a good place to be. All right, so let's break down how we've done this. So there's two concepts we've paired together to do it. First is something that's probably familiar to most people here, in just a normal circuit breaker. Everybody's got a circuit breaker box in their house. It detects when there's a short in one of your appliances or there's a surge somewhere, shuts off the power, opens the circuit, or breaks the circuit, so to protect the circuits, right? So it protects all the rest of your devices. You go and unplug the faulty device, turn the circuit, or flick the switch to close the circuit, lets power flow, all that sort of stuff. So that's pretty standard, right? And there's a bunch of published material on this on the internet, so there's not too much that we're doing that's new there. But what is different for a circuit breaker and not standard is the inputs you have into your circuit breaker. What are the conditions that will trigger or break the circuit? And what are the conditions that you use as input to restore and resume the circuit? So the second one that we're going to pair into this is called a token bucket. Now, token buckets are sometimes used for retries, but more commonly they're used for networking. The internet connection here will have some form of a token bucket. Every device that you own will have some form of a token bucket implementation in it. And it's just a way of managing or limiting concurrency. So let's say you had a bucket with 10 tokens in it. That means that 10 people could take a token and go and enjoy a ride or do something. The 11th person has to wait for one of the other people that are out there to come back and put the token back in, and then they can have their turn. In a networking scenario, let's say you wanted to limit your downloads to 100 kilobits a second. You'd put 100 tokens that are all a kilobit each into the bucket. Therefore, you can only have 100 going at once. Right? So it's used more to rate limit is effectively what it's for. So you can probably see where we're going with this, right? We take that token bucket and we use it as a signal into the circuit breaker. Really simple in theory, but up until a couple of months ago, there was no published material on people doing this. And now when I checked yesterday, someone has published something a couple of months ago, a theory on this, but it's behind Substack and I'm not paying for that. So I'll get work to pay for it. So it's not a common thing, and I don't think I've seen anybody do this, especially in mobile, just yet. So kind of trying it out here and seeing how we go. But the beautiful thing about this is that last line. Regardless of how complicated your situation gets, all you're doing is managing the flow of tokens in and out of that bucket. You can change your inputs, you can change your conditions, you can change the size of tokens, whatever you need to do to manage that flow, but it doesn't complicate the rest of the code that sits around it. So it's actually only about 100 lines of code to do what we did before. And it's effectively two functions. One function for withdrawing a token and scheduling a retry, and one function for depositing a token and then kicking off anything that's pending. So how do we put this all together? My laptop's gone to sleep in front of me again. So we use a two-tier or hierarchy of buckets. Normally, when you do this sort of thing in networking, you have a trickle-down effect between your buckets. We have two separate, distinct buckets. We run them in parallel for different purposes. The top-tier bucket is typically API-specific, or retry-specific. It has a unique name or identifier associated with the retry. If you're retrying an API request, it's probably sensible to use the URL of the API that you're retrying, so you always have consistent to that URL. And then the second tier is the circuit breaker. Now, in most apps, I would say that try this. The circuit breaker would be global. But if you have one set of APIs that live on one infrastructure and one set of APIs that live on a completely different infrastructure, you might want to put them into separate circuit breakers, because there's chances of them both being, impacted at the same time is low. But most importantly, I wanted to call out that this governs retries only. It doesn't stop the user from doing something. It doesn't stop the app from doing something. It just controls the automatic retry. And that becomes important for recovery later on as well. If the user attempts something and it succeeds, there's a good chance we can attempt something and it can succeed too. I'm going to stick with this one. All right, so we're into the final stretch. So let's say, I think that's the wrong notes, but anyway. So let's say we have a failed API request, right? And we want to model how this is going to work. On the screen, you'll see a really simplified scenario. I've got 4 API-specific buckets and 1 circuit breaker. The API buckets start with 7 tokens in them, and the circuit breaker starts with 21. I'll get to how we get to those numbers later, but consider the buckets are full at this point. Let's do this one. Right, so let's say API 1 is failing. It's returning a 500 internal server error. We have plenty of tokens, so we go ahead and withdraw 1 from both the API-specific bucket and the circuit breaker, and then you can go and try. So as I said, we run them in parallel. Let's say it fails again with another 500 internal server error, comes back in. Well, we still have 6 tokens in the its bucket and 20 in the circuit breaker, so we can just go ahead and do that again. But we already know that retries are selfish and we want to slow them down. So we can use, so we know there's 2 tokens missing from bucket 1. So we can use that to apply our exponential backoff algorithm that we had before. 2 tokens missing from the bucket means we would wait 1 second before retrying. And then on the next one, if there's 3 tokens missing from the bucket, we'd wait 2 seconds, and then 4 seconds, 8 seconds. Don't need to step all the way through that, right? All the way up till we get to 32 seconds. So let's assume we went that far. And now we've run out of tokens on API 1. We can't retry anymore. There's no tokens. It's done. That's been a very naughty API. It can be decommissioned and we'll never talk to it again. Sadly not. The user is still waiting for their data, right? So we need another input of tokens to be able to continue our retries. If we want to continue the same experience we had with the exponential backoff, we want one token every 30 seconds or so. So why don't we just deposit 1/30th of a token every second? And now we get to sit here while I do a 30-second animation. No, we'll speed up time. Great. 30 seconds has passed. We have a token. That means we can retry that request and we can go again, right? If it keeps failing, we'll get another token into the circuit breaker bucket and then, into the normal bucket every 30 seconds. So we can still continue those retries. So in that way, when one API is failing, it functions the same way as the exponential backoff because we have a new token every 30 seconds. All of the other APIs are unaffected. They've got plenty of tokens if something goes wrong. So, it's quite happy. Once one of those retries succeeds, then the API request that succeeded will put the token that is borrowed back into the original buckets that they came from. So as we succeed, we return the tokens. We're really just borrowing them, hopefully, to succeed and return them, right? So we call the top row the rate limiting buckets because they control the overall rate of retries. If the API is flaking and going up and down, the overall delay and rate of those retries is managed from that bucket. So if it were to fail in this scenario, we're already missing 4 tokens. So we would wait 4 seconds before our first retry, right? We give the API in theory 3.5 minutes based on our 30-second rule for the bucket to be full again before we consider it healthy. All right, so let's talk about the circuit breaker bucket. As I mentioned, we run the 2 buckets in parallel, and we withdraw and deposit from both at the same time. Both buckets need to have enough tokens for the retry to be emitted, and both get notified when we succeed. So previously, when there was only one API failing, we never really got below 14 tokens in the bucket. If we had 2 APIs failing, we'd never really get below 7. And it's only when we have that third API failing that we would consider the circuit to be, we've reached that threshold. That's what our configured threshold is. And that means at a normal exponential rate, it takes about 60 seconds to get through the 7 tokens. So if you've got 3 APIs failing, that means you've had 3 APIs failing for a minute, or just over a minute, before we consider it a severe enough outage to break the circuit and stop other retries and protect the backend from that. But if we had 4 APIs failing, then it would be 30 seconds. If we had 5 APIs failing, it would be 15 seconds, so on and so forth, right? If you have 30 APIs failing, it's going to be pretty much straight away, because you already have 21 tokens in the circuit breaker bucket, and all of them will go immediately. So let's say that happened, right? We've big enough problems going on, we've broken the circuit, there's no tokens available. At this point, any retries that came in would fail. Like we can't do anything with those. Regardless of whether it's API 4 and has tokens in its bucket, the circuit breaker doesn't. So we've tripped and we're not doing that anymore. So in this scenario, we don't schedule any more retries. They go into a queue to be retried instead. And it's a prioritized queue, and I'll get into that, right? So that means every 30 seconds when we deposit tokens into the circuit breaker in the normal bucket, we have enough tokens to retry 1 request. And it will be the highest priority request that we have. So let's say you have a really important API that you use, maybe one that you use to manage the rest of your cache, your stream that handles your caching validation. That's probably your most important API, so you make that your highest priority. That means in the full outage scenario, you know which API is going to be called every 30 seconds. So you can see that coming through, right? And then you can use that as your signal to determine the health of the rest of it. So let's say 30 seconds has passed. We have a token in the circuit breaker bucket, so we can take the highest priority retry, we can give it a go. Unfortunately, it doesn't work, right? So a new retry is requested. It's still the most important one, so it goes straight back to the front of the queue. This time we have 30 seconds pass. Here we go. And we can go again, right? Same as before. But this time it succeeds. So it takes the token that it borrowed and it puts it back in the circuit breaker, which means we can then retry the next one and it puts the token back. And we can retry the next one and it puts the token back. And by this way, we can, over time, one at a time, go through all of our pending retries and restore service without slamming the backend with 30 API requests all at once. So we're pretty much at the end. As I said, there's 2 functions that are involved. This one, before withdrawing tokens, we really, whenever you try and attempt a retry, request a retry, we check if both buckets have enough tokens. If they do, we use the tokens, or we withdraw the tokens, debit the tokens, use the rate limiting bucket tokens to calculate the delay, and schedule the retry. If there's not enough tokens in either bucket, it just goes into the queue to be retried for when there is enough tokens in the bucket. And then the second function is depositing tokens. We deposit the token. If it's the 1/30th of a token that we deposit every second, it goes into every bucket. If it's one for the notification of a successful retry, it goes back into the buckets that we borrowed it from so that they can be reused for the next one. After that, we just sort any pending retries by priority, and then we just iterate over it. If they have enough tokens to try, we debit the tokens, execute that retry request, move on to the next one, so on and so forth. And that's really all there is to it. And we've reached the end. So, as I mentioned, all the QR codes for the relevant articles and references and previous talks are on the screen if anybody's interested in any of those.